So, dear students, I will welcome you today for the understanding of conduction. First, what is conduction that we will see by certain experiments. Now, if it is a metal piece and if it is heated on one end and we have fixed a wax on the another end and started heating, initially this wax is a solid, and once we have started heating it, heat energy that is getting transferred, the temperature of this metal strip that will increase gradually, the sufficient heat will reach to the another end, and as a result this wax will melt. But if you do the same experiment with a wood, then it may take a much higher time. So, the metals are good conductors of heat. That is because the metals have atoms inside them and lots of free electrons. That is, the atoms and the free electrons are there. And these free electrons can move around and vibrate very easily in the metals. So, the heat energy is possessed by the neighboring particles vibrating along inside the metal. They vibrate and transfer their energy to the other. Yesterday we have already talked related to the temperature. Temperature is nothing but the kinetic energy, the energy in action, that is nothing but your kinetic energy, and this kinetic energy that is responsible for transferring of vibrations. Because of the vibrations, they transfer their energy to the adjacent free electrons, and as a result the kinetic energy transfers from one end, which is getting heated, to the another end. Now, with in this cold season, if you are sitting on a metal chair or if you are sitting on a wooden chair, you can significantly observe or note the difference of temperature of the metal as well as the wood. If it's a metal, then it is a cooler. However, the temperature of the wood, that is somewhat warm as compared to the metal. The wood feels warmer because it is a poor conductor. It cannot conduct the heat away from our hand as quickly as copper, which is a good conductor, and that is why this difference is observed. So non-metals are the poor conductors of heat. In a non-metal, heat energy is only passed on by neighboring particle vibrating along the non-metal, which is a non-free electrons. That is the limitations. This allows a flow of energy from hot to the cold. Then similarly, for the liquids also, can we do the certain experiment? Now this is in a test tube, the water that is available and a certain mesh or a gauze that is put here, and here we are holding a ice block, ice cube, and this ice cube is not allowed to move in the upward direction. That is why we have kept this gauge, and we are heating the upper part of, so that the water that will be heated, so the temperature of this upper part of the water that will increase, and slowly it will transfer its heats to the lower part. That is why we have hold the ice cube in the lower part. If and observe the time to melt this ice cube. Now, second condition, that is, instead of putting this gauze, we have allowed this ice cube in the upper region. So you can note down the difference to melt this ice cube. That is, the liquids, they can transfer, they can conduct, but with a less rate. So liquids are poor conductors of heat, that is the good insulators. Similarly, the gases, they are also the poor conductors of heat. So metals, very good conductors, non-metals, insulators, liquid insulator, gases, good insulator. However, vacuum, they are the excellent insulators. That is why in a thermos flask or your thermosteel water bottles, the vacuum that is available. Now, these are all the bottles which we use, they are double layered bottles. That means the one layer which is there from the outside we can see, and inside also there is the another layer of a metal, and in between these two layers there is provided a vacuum. If you hit it and observe the vibrations, vibrating sound, you can feel the two metals or resonance sound that you can listen to certain extent. And this vacuum that is provided, and that is why they are providing or keeping the water hot or water cold as per our requirement. So this excellent vacuum that becomes a good insulator. Similarly, in certain plastic bottles also, we put the polyurethane foams as the insulating material, and that is also helping us to maintain the temperature to a certain time. But when we are using this metal and as a vacuum, as an insulation purpose, the duration becomes more, the time factor is more. That is why some companies, those companies which claim that the water can remain hot for say 24 hours, that means they are providing a better vacuum in that double bond layered insulation. Similarly, in case of your physical chemistry experiment also, you must have done the experiments of a calorimeter. Calorimeter that is also contains insulating thermos flask that also keeps the temperature, maintains the temperature. Then how are the particles, they are arranged in solid gases that you know. So when the metal is heated, the free electron gain the kinetic energy. When metals are heated, the free electrons gain the kinetic energy. This means that the free electrons moves faster and transfer the energy through the metal. Free electrons move faster and transfer the energy through the metal. This makes the heat transfer in metals very efficient. Insulators do not have the free electrons, and so they do not conduct the heat as well as that of the metals. So we can define this the flow of heat in a substance due to the exchange of energy between the molecules having more energy and molecules having the low energy. That is what the conduction, the exchange of energy with the higher energy to the lower energy molecules, and that is what the conduction is taking place, the transfer of heat from one particle of the matter to the another by direct particle to particle contact. That means here the physical contact that is necessary. So conduction occurs primarily in the solids because the particles are tightly packed together and available with the free electrons. The particles themselves do not change their position. However, because of the vibration, they transfer their energy to the adjacent molecules. So the particles absorb the energy and vibrate faster. They collide with the other particles. As a result, the energy is transferred to the other particles and they begin to vibrate more rapidly because gaining the energy increases more vibrations, and as a result the temperature, the noted parameter, that is the temperature, that will be that one can observe the difference in the temperature. So particles absorb the energy, vibrate faster, they collide with the other particles. Because of the collision, because of the momentum transfer, the other particles also start vibrating, and the difference in the temperature that can be noted because of the temperature, because of the vibrations. So defining this conduction, the passage of heat from one part of a substance to the another part of a substance, or from one substance to the another in physical contact with or without the movement of particles of either substances. That means that can be in a single substance or the physics substances which are in physical contact. Then the conduction that can takes place. So you can say that all the metals such as your silver, copper, brass, iron are the good conductors as compared to your non-metals. Metals vary in their respective ability to conduct the heat, and this ability or inability is referred to as the conductivity. So the ability of the metals to conduct, that is the conductivity. This physical property to conduct the heat is called the coefficient of thermal conductivity of a material. So the another term in addition to the conduction is the thermal conductivity. It's the ability of a material to conduct the heat. So this physical property to conduct the heat is called the coefficient of thermal conductivity of the material. So conduction, that is the process whether the heat is transferred directly through a metal with any bulk motion of the material playing no role in the transfer. That is what the limitation. Bulk motion, physical movement नहीं हो रही है. That is the vibrations of the atoms or molecules that is going to lead the collisions. Because of the collisions there is a transfer of energy that is taking place. No physical movement, material bulk movement is not there. Those materials that conduct the heat well are called the thermal conductors. Huh. So now consider this is certain geometry. On one side it's a warmer body, heat flows from higher temperature to a lower temperature. The other end is the cooler body. The amount of heat, this is the amount of the heat, that is having the unit of the joules, conducted through a bar from the warmer end to the cooler end depends on the number of following factors. That is, it is proportional to the time, first thing, because here we are considering the amount of the time, amount of the heat. So, and its units are joules. So it is proportional to the time. Then it is proportional to the temperature difference between the warm body and a cooler body. वार्म बॉडी एंड अ कूलर बॉडी, उसका जो टेम्परेचर डिफरेंस है वो अकाउंट होगा. सो अमाउंट ऑफ द हीट is proportional to the temperature difference delta T between the two ends of this bar, and it depends on the cross sectional area through which the available area the heat is getting transferred, and also it is inversely proportional to the length L. कितना डिस्टेंस उसको ट्रैवल करने का है उस हीट को, उस molecules को energy because of vibrations, how much time that is required, between what temperature difference it has to transfer, through which area it has to transfer, and how much distance it has to transfer. So Q, the amount of heat, is proportional to the cross-sectional area A of the bar and is inversely proportional to the length. So one can write amount of the heat is proportional to A delta T into the T time upon the L. And here the proportionality constant K, that can be added as your thermal conductivity. Thermal conductivity, it's the ability of a material to conduct the heat. So note that the heat flows increases with the increasing temperature difference, increasing the surface area and decreasing the thickness. So increasing the area, increasing the temperature difference, increasing the time, and is inversely proportional to the length. So length increases, your amount of heat transfer that decreases. So the conduction that can occur because of the molecular vibrations and because of the free electron diffusion. Yes, the this the same is the called the Fourier law. That is the Q. Here is the heat transfer rate. That means capital Q upon T time, and it is having the units of watt per joules per unit time. Q per unit time, that is what? Joules per second. That is nothing but your watt. So heat transfer rate, this is what? The rate Q and having the unit of watt. This is K A dt upon dx. We have taken the delta T, the temperature difference between the 2 points T1 to T2. So dt, that can be written as T2 minus T1, and d delta x, that is nothing but your length L, that can be taken as in the meter. This is in the Kelvin, this is in the meter, then A is your meter square. So the thermal conductivity K, that will have the units of watt per meter Kelvin. Watts per meter Kelvin. By simplifying this equation, you will get the units for thermal conductivity K, that is the watts per meter Kelvin. So Q, amount of heat, that is units joules. Amount of the heat transferred per unit time, that is the joules per second, that is nothing but the watts, and this is equal to Ka dt upon dx, and this is known as the Fourier law of heat conduction, or the conduction law, or the Fourier law, where K is your thermal conductivity, that is the ability to transfer the heat, that is having the units of watt per meter Kelvin. Now the next terminology, that is the heat flux, that is the heat transfer rate per unit area. This is nothing but the Q upon A. This Q upon A, that is the heat flux, which is equal to K dt upon dx. So Q having the units of watt divided by the area, that becomes your watt per meter square, and watt per meter square is nothing but the heat flux. Watt per meter square is the heat flux. So we are having the three terms, that is the Q, amount of the heat, then small q, heat transfer rate, unit is watt, this is nothing but the joules per unit time, and the heat flux, that is the watt per unit area, that is the small q upon the area, and the fourth is your K, thermal conductivity, watt per meter Kelvin. You must remember all these units in detail. So molecules are in constant motion. Their speed is proportional to the temperature of the object, that is related to kinetic energy. When two objects come in contact, the surface molecule will transfer the momentum, transfer the energy, and that is why you observe the increase in temperature. An aluminum pot will conduct the heat from the glass stove top. Now the thermal conductivity, that is also there. The conductive transfer, that is also called. So this is in other terms also the transfer of energy from the more energetic particles of a substance to the adjacent less energetic one as a result of interaction between the particles. That is what the another definition of the conduction that can be also done. Transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones. So rate of heat conduction, that is nothing but is proportional to the area, temperature difference, and the thickness, that is what is proportion, and having the proportionally constant K as your thermal conductivity. Now in this case, your metal strip that is taken into account, because generally we are either doing this type problems associated with this type or the previous figure which we have already seen. That is T1 and T2 are the temperature differences. The this temperature difference, higher temperature minus the lower temperature, that is what is taken, and here the minus sign that is adjusted as delta T is T2 minus T1. So the thermal conductivity, a measure of the ability of a material to conduct the heat. Now in this figure, from 30 degrees Celsius to 20 degrees Celsius, the heat temperature drop that is there. If the distance that is say 1 meter, how much amount of the heat that can be transferred, that can be easily calculated by using this formula Q, which is equal to Ka dt upon dx. Temperature difference is there, the length difference is there 1 meter, K that is provided as the 401 watt per meter degrees Celsius. So I can put all this K 401, area that is the 1 meter by 1 meter that can be taken per unit per meter square, and dt is the temperature difference. Now here 20 minus 30, that is minus 10, so this minus minus sign that becomes the positive, and you can have the value of Q that is 4010, right? This already also one can do it. This is the simple problem using the Fourier law of heat conduction, basic formula of conduction that is needed. Then the thermal conductivity, the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. What this definition is associated, that is the watt per meter degree Celsius or watt per meter Kelvin, right? The heat rate of heat transfer. Rate of heat transfer is what? The watts. Rate of heat transfer through a unit thickness per unit meter. It's a unit thickness of a material per unit area per unit temperature difference. So thickness upon the area, thickness upon the area, that is the meter per meter square, that will reduce as the meter. So unit of thermal conductivity is the watt per meter degrees Celsius or degrees Kelvin. The thermal conductivity of material is a measure of the ability of the material to conduct the heat. The higher value of thermal conductivity indicates that the material is a good heat conductor, and a low value of the indicates that the material is a poor heat conductor or a insulator. So how to select this insulator and the conductor, that depends on this value of conductivity, thermal conductivity. You can see the diamond that is having the highest thermal conductivity of 2300 watt per meter Kelvin. Then silver that is having the value of 429, copper 409. Now water that is having the 0.607, then air 0.026. One has to remember these values for air, that is 0.026 watt per meter degree Celsius, then water 0.607 watt per meter degree Celsius, then probably the copper and iron or steel that you may require. Then your polyurethanes, that is also having the thermal conductivity of 0.026, and if it's a vacuum, then again its value is very low. The next is the thermal diffusivity. That is, alpha is nothing but the thermal diffusivity, which is the K upon rho Cp. K is thermal conductivity upon the rho Cp. Rho Cp is the heat storage. Cp is your heat capacity per unit volume. Rho Cp is the heat capacity per unit volume. So Cp is the specific heat capacity per unit mass, and rho Cp is the heat capacity per unit volume. That is what the thermal conductivity represents, how fast the heat diffuses through a material. How fast the heat diffuses through a material. So कोई भी मटेरियल है उसमें से if it is a metal piece, then how fast that material allows the transmission of the heat from one point to the another point to the next point. This is what the diffusivity, thermal diffusivity. When we talk a thermal diffusivity, it's a temperature that is being getting diffused, the heat energy that is getting diffused. It represents how fast the heat diffuses through a metal. So it's a, when you one can say the physical significance, it's a, it tells how fast the heat is propagated or it diffuses through a metal during the change of temperature with time. During the change of temperature with time, कितने टाइम में कितना टेम्परेचर चेंज हुआ है, that is to be noted or understood with this thermal diffusivity. The larger the thermal diffusivity, the shorter is the time required for the applied heat to penetrate deeper into the solid. That means the higher the value of the thermal diffusivity, the shorter is the time required. That means it can very easily diffuse. That means the temperature that can be very fast transferred. Shorter the time required for the applied heat to penetrate deeper into the solids. The material that has a higher thermal conductivity or a low heat capacity. Now looking to this formula, that is K upon rho Cp. If K is having the higher values, then this thermal diffusivity will also have the higher values. So it depends on the thermal conduction. If the higher is the thermal conduction, then the thermal diffusivity will also be higher. But it is inversely proportional to the heat capacity. That is the heat capacity per unit volume. So lower heat capacity will obviously have the larger thermal diffusivity values. Lower this value of rho Cp, higher will be the value of alpha. So the larger the thermal diffusivity, the faster the propagation of heat into the medium. Propagation of the heat, the diffusion of the heat, that is to be indicated or concerned about the thermal diffusivity. The small values of the thermal diffusivity means that the heat is mostly absorbed by the material and a small amount of heat is conducted further. Mostly the heat that is absorbed. That means the higher the value of Cp, higher the value of specific heat is, that is going to absorb the heat. And as it is going to absorb the heat, there is a less diffusion that is going to take place. So the units of thermal diffusivity, that is meter square per second, heat conduction upon the heat storage, K, that is the units of watt per meter degree Celsius, and rho Cp is the joules per meter cube degree Celsius. So it becomes equal to meter square per second. K is the thermal conductivity.